Hey, today we're going to talk about mass, weight, and gravity. After this video, you should be able to explain how mass and weight are related to each other, explain where gravitational forces arise from, develop and use a universal and local model of gravity, and apply that local model of gravity to understand the motion of an object in freefall. So let's start with mass and weight. They're different from each other. Mass is how much stuff or how much matter you're made out of. Weight is the gravitational force of attraction exerted on one object due to another object, which is usually a large body, in our case, the Earth. So if you were to get on a bathroom scale, what are you measuring, mass or weight? Well, the way a scale works is you stand on it. You interact with the scale by applying a force to it, which in this case, if you stand still and nothing else is happening to you, happens to be the same force as the force of gravity. The scale squishes a little bit and takes a reading and measures that force. So a bathroom scale measures your weight. Now, if you were to use a triple beam balance, which is a balance like the scale a doctor uses to measure you, where you have some little masses that you slide along and you balance them out like a balance beam, what do you think that measures? Well, that actually measures your mass. It doesn't measure your weight. Your mass is pretty much hanging from one end of the scale. These other little masses are hanging from the other end of the scale. You place them in a certain spot until everything is all balanced out, and depending on where the spot is, the scale tells you what your weight is. So even though this thing tells you your weight, it's actually measuring your mass, and it kind of has a built-in conversion to get your weight out of it. So mass and weight are related to each other, but they're not the same. So the full model for the force of gravitational attraction between two objects was found by Isaac Newton, and it looks like this. It says that the gravitational force of attraction is proportional to the mass of each object separately, and it's also inversely proportional to the distance between the two masses squared. And you have to throw a constant in there to make all the units work out correctly. And when Newton came up with this, he really had no idea why this was the case. But he measured things, he figured out that this works great, this model of gravity is amazingly accurate, but at his time he actually had no idea at all why objects acted this way. And now we know a little bit more with some work on quantum mechanics and the standard model of the atom. We kind of know how massive objects interact, and there's even some research being done right now trying to find something called the Higgs boson, which might give us some more idea of how massive objects interact. But for now, we're going to use Isaac Newton's model, which just says the gravitational force of attraction equals a universal gravitational constant, capital G, times the mass of object 1 times the mass of object 2, divided by the distance between the two objects squared, which is r. So if we look at this closely, it's a little bit complicated, and in our first level physics class, we're not going to really use this full model too much. We're going to develop it into a more simple model that works great when we're on the surface of the Earth. So we'll get more into this if you take AP, but right now let's think about the surface of the Earth. So if we say the two objects that are interacting, one object is U, little m, and the other object is the Earth, capital N sub E, the mass of the Earth, what variables in this equation remain constant for different masses on the surface of the Earth? So think for a second and see if you go from your mass to your girlfriend's mass, to your boyfriend's mass, to your dog's mass, to your book's mass, what variables in this equation actually don't change when you change those situations? So all it's really changing is your mass, so everything else is going to stay constant. So the universal gravitational constant doesn't change. The mass of the Earth doesn't change when you go from person to person. And if everyone's on the surface of the Earth, no one goes really, really high up into the mountains or really, really far underneath the ground, the distance between you and the center of the Earth doesn't change either, so r stays the same. So see what happens if we put these three variables together. So the universal gravitational constant, capital G, is 6.67 times 10 to the negative 11th meters cubed per kilogram second squared. Mass of the Earth is roughly 6 times 10 to the 24th kilograms, and the distance between the center of the Earth and the surface of the Earth is about 6.4 million meters. So if we put these three variables together, do a little bit of math, the value of the constant we get is actually 9.8 meters per second squared. Well, hey, this is something we've seen before. This is the value of the acceleration of objects on the Earth that are in free fall. So this is what we used to call the acceleration due to gravity. Well, in this case, we're going to give it a little bit different units. I'm going to call this thing little g now, since it's a different type of constant. It's the Earth's special local gravitational constant for anything that's on the surface of the Earth. And I'm going to say little g has a size of 9.8 newtons per kilogram, or a lot of times we just use 10 newtons per kilogram. And this tells me basically how much force of attraction in newtons I get for every kilogram of mass that is on the surface of the Earth. So if I'm a 2 kilogram person, I would have 19.6 newtons of attraction. If I'm a 10 kilogram person, I have 98 newtons of attraction to the Earth. And remember here, take note, capital G is a universal constant. It's the same everywhere you go in the universe. A little g is not universal. Little g is a special gravitational constant that's local to the Earth itself. It's only good at the surface of the Earth. For example, if I go farther up into the mountains somewhere, the mean distance between me and the center of the Earth is actually a little bit bigger. Therefore, my local gravitational constant, which remember is capital G times the mass of the Earth divided by the distance between you and the Earth squared, is going to actually go down a little bit. So the local gravitational constant can change depending on where I go on the Earth. If I go out in space somewhere, that goes down even farther. It doesn't go to zero. It's just the distance between me and the Earth gets bigger, so the local gravitational constant actually goes down. Now let's look at this equation again. So this tells me how big of a force of attraction there is between me and the Earth. And I use it to tell me how hard the Earth is basically pulling on me. But we know from Newton's third law that for every force there's an equal and opposite force. What does that really mean? Well, that means I'm also pulling back on the Earth. My question is, why doesn't the Earth then jump up to me? Why, when I jump out a window, do I move down towards the Earth as opposed to the Earth moving up towards me? Well, we also have Newton's second law that says the sum of the forces equals mass times acceleration. And if the only force we're dealing with is a gravitational force, that gravitational force on me may make me accelerate at a rate of 9.8 meters per second squared, but that exact same size force on the much more massive Earth is going to make it accelerate a lot less. And this acceleration is so small that it's not even perceivable by anything in the universe right now. So we are really pulling up on the Earth, just that pull that we apply on the Earth does that pretty much nothing to the Earth, where that same pull on us makes us fall down at a rate that could actually kill us depending on how far we fall. All right, so we said that we put those constants together, we get a local gravitational constant. So we have a new model for gravity, a local model for gravity that says the force of gravitational attraction between two objects equals the mass of one object times the local gravitational constant due to the other object. And again, if you don't really move, if you don't change your distance between the two objects too much, that local gravitational constant stays fairly constant. So the Earth has one. We use about 10 newtons per kilogram. Other planets or objects have one. The moons, for example, is about 1.6 newtons per kilogram. Jupiter is about 26 newtons per kilogram. And the local gravitational constant on the surface of the sun is about 275 newtons per kilogram. But now we said this works for any massive object. So that means there's also going to be a gravitational attraction between two people. Now, two people they have mass. They're going to have a gravitational attraction between each other. So that means, yes, the cute girl in class that you tend to like, she actually is attracted to you, because you have your own local gravitational constant associated with you. So if that girl walks up to you and is about a foot away from you or a meter away from you, let's say, you're going to have a gravitational force of attraction to her, and she's going to have one back to you. Unfortunately, you're not as attractive as the Earth is. Your gravitational constant, your local gravitational constant, is only about 0.000000005 newtons per kilogram, or about 5 times 10 to the negative 9 newtons per kilogram, which is about 5/1 billionth of a newton per kilogram. So unfortunately, your force of attraction to the ladies and to everyone around you is not very big. So I guess you have to rely on your personality instead. So one special consequence of gravity for massive planets is this thing we call freefall. So here we have a red sphere. Let's assume it's on near the surface of the Earth, and we let it go. and we want to figure out what's the acceleration of the sphere. And you might say, hey, I know what that is. I know this answer right now. But let's work through it and see if we can figure out where that answer came from. So if we want to draw a free body diagram of this object, we only have one force acting on it, the force due to gravity. If we use Newton's second law, it says the sum of the forces, in this case is just the force of gravity, equals m times a. We substitute our new model for gravity, which is mg, into this. We get that mg equals m times a. There's an m on both sides, they'll cancel out, and we get that g equals a. So there's kind of the proof why our acceleration due to gravity is the same as our local gravitational constant. But remember, they're really not the same thing. Our local gravitational constant g and our acceleration due to gravity may be the exact same size, but they really stand for different things. G stands for the local gravitational constant of some massive object, and A stands for the acceleration of an object when the only force acting on it is the force due to gravity of that object. So yes, in these cases they'll be exactly the same size, but they don't really stand for the same thing. That's why I like to use, to kind of keep them separate and say that G equals 10 newtons per kilogram on the Earth, surface of the Earth, and the acceleration due to gravity on the surface of the Earth is 10 meters per second squared. Even though newtons per kilogram and meters per second squared are the exact same unit, these are the exact same size, they do mean different things, so it's usually useful to keep them separate by calling them different things. So hopefully after going through this, you've learned a little more about weight and mass and the force of gravity. You can explain where these gravitational forces arise from. You understand what the difference between a universal gravitational constant and a local gravitational constant and how you can find a local gravitational constant. And you can now apply your local model of gravity to force problems to solve for things that are in free fall and other types of problems.